2.3 is on inverse and transpose. All right, so we're going to start with something that we just finished doing, which is finding A times B and B times A.
Is that minus 3 or 3?
Oh, minus 3. Minus 3. Yeah. It still doesn't look better, I get it. It is a minus 3. So we just finished doing this A times B and B times A, and at the end of the lecture I said what? When could they be equal? And that is when they're inverses. Okay? So, assuming that we wrote minus 3 and did this correctly, what are we probably going to get when we multiply them? The identity. So let's see. So 1 times minus 3 plus minus 2 times minus 2. So this is minus 3 plus 4 is 1. So far, so good. 1 times 2 plus minus 2 times 1. 0. 2 times minus 3 plus minus 3 times minus 2. And the last one, 2 times 2 plus minus 3 times 1. Is 4 minus 3 is 1. So we got the identity. And make sure you get your words straight, inverse and identity, because the I does not stand for inverse. The I stands for identity, and there are two words, they both start with I, so be careful of that. We don't need to calculate B times A. If you get A times B to be the identity, then the other way is also the identity, because they're inverses of each other, right? If you get that. So we actually do not need to calculate the other way. We would just say B times A is also equal to I. You could give the matrix if you wanted to, but if they multiply one way and get the identity, then they multiply the other way and get the identity. Okay, so that's one. So they are inverses of each other. So we could say that B is A inverse, or we could say that A is B inverse, and both would be true. Right, they are the inverses of each other. So how do we actually compute and find the inverse? So I gave you an A and B here that didn't have fractions in it, but most of the time, remember it's like dividing, most of the time you actually have fractions in your inverse. Okay, and there's only a special case where there's not a fraction in your inverse. Okay, so how to find the inverse of a 2 by 2 matrix? First, we need to find what's called the determinant. Okay, And the determinant is just a number that tells us something about the matrix, okay? So the determinant, we're just going to look at 2 by 2 because there's actually a little formula to get the inverse of a 2 by 2, and to find the inverse of a 3 by 3 or 4 by 4 is much harder, but a 2 by 2 is really quick. So first we need to find what's called the determinant. So the determinant of a matrix A, B, C, D is, all right, now be careful. This is a matrix with square brackets. I didn't put square brackets here, I put absolute value brackets, just straight lines. That symbol is determinant. Okay, so we saw it before when we did cross product. So what was the cross product? What did we do? Right, A times D minus B times C. That number is called the determinant. So we used that determinant technique when we found the cross product earlier. When we wanted to find the cross product of 2 vectors, we put them into a matrix, and then we did the little cross products of them. So that cross product is actually the determinant. So, matrices, not all matrices have a inverse. So, a square matrix has an inverse if the determinant of the matrix is not equal to 0. So these are the 2 ways to write the determinant of A. You can write det A. A can be in a bracket or not, doesn't matter. Or those absolute value brackets. Those symbols both mean determinant. Okay, so 2 different ways to say the determinant of A. So as long as the determinant's not 0, so if the determinant then A is said to be singular and has no inverse. If a matrix is non-singular, it has an inverse. And the determinant of A is not 0. So I want to say that sort of both ways. So singular, to remember, like I say, if you're single, you don't have a partner, right? So if a matrix is singular, it has no partner. It has no inverse. Does that make sense? Okay, so just to remember that the word singular, show that the matrix is singular. What would that be asking you to do? Find the determinant and say that it's 0. That's really it. Or try to find the inverse and it won't work. That would be the long way to do it. But so if you want to show that something has an inverse, you find the determinant. There's a whole chapter on determinant, or a whole section, so we'll do that later. But we're going to just show you how to find it quickly now. Okay. So, whoops. A times A inverse is equal to A inverse times A, which is equal to I. What about A inverse? What do you think? A, yeah, good. Take the inverse and then the inverse again, you'd be back to where you started. Okay, so to find the inverse of a 2 by 2 matrix, so what did I do to matrix A? This here is what? 1 over the determinant of A. Right? 1 over the determinant of A. And here, what did I do? It was A, B, C, D. So I switched the A and the D, switched them around, changed their place. And then change the sign of these two. Okay. Now what does that do? Well, if you're thinking about matrix multiplication, when you multiply, say you had a row, 1, 2, and you're multiplying by a column, if the numbers were reversed, so you'd go 1 times 2 and 2 times, one of them would have to be negative. So you need to switch a sign and switch places. That flips them over so that you get 2 times 1 and 2 times negative 1. So switches the sign and flips the place of the other one so that when you put them together they will equal 0 or 1, whatever you're looking for. Okay, so this is the method. So D, A, so those are switched, and these two have the sign opposite. And if you switch the wrong ones and flip the sign of the other ones, it won't work. So you do have to remember. So the main diagonal is the one that you switch the places of, and the other ones you change the sign. Okay, so if we look at that matrix that we had earlier, A was 1, minus 2, 2, minus 3. And B, yeah, it was that negative 3, whatever we had earlier. So what's the determinant of this? So the determinant of A is 1 times minus 3 minus, you subtract going backwards, minus 2 times 2. So minus 3 plus 4 is 1. So I said only sometimes there's a special case when you don't have fractions in your determinant, and that's when or in your inverse, and that's when the determinant's 1. Because now we would say the inverse is equal to 1 over the determinant, which is 1. Switch the place of the main diagonal, so minus 3, 1, and change the sign of these two. So it almost looks like we switched them, but. So the inverse is minus 3, 2, minus 2, 1, which was equal to B earlier. We already checked it. So to check, you would multiply them together and hopefully get the identity. All right, so example. One, 2, 0, 3. Okay, so first find the determinant. So find the determinant of A, which is 1 times 3 minus 2 times 0. Right? And then you write your inverse. So remember it's D, A, minus B, minus C. Switch the place and just change the sign. So 1 over 3, 1 over the determinant. And then if we switch these two, that will be a 3 and a 1, and change the sign of these, so minus 2, and 0 would still be 0. Multiply that in. So 3 over 3, minus 2 over 3, 0 over 3, and 1 over 3. So multiply them either direction, it doesn't matter, because if that's the inverse both ways, we'll give you the identity. In fact, if you've got a whole bunch of fractions here, what could we do?
Divide it.
Take that out to the front as a scalar and then put it back in later, which is what I always do. But if you just multiply A times A inverse, you should end up with the identity. Another thing is that if there's fractions in here, if you leave them with a common denominator, it's better again, because when you do your multiplication, you'll already have them over the same denominator. So fractions are easier. But you could leave it like this. That's a scalar multiple. Multiply that and then put the 1/3 in. That would work as well. All right. 1 times 1 plus 2 times 0 is 1. And let me comment on this, actually. So suppose we're going along and we get a number. We're checking our inverse. The bigger ones get harder. So we're checking our inverse and we don't get a 1 or a 0. So, of course, you have to go back and find your mistake. Suppose you can't find your mistake and it's a test, like the final exam. What could we do? So just because I see this a lot, so in a 3x3, it's like a whole page of steps to get the inverse of a 3x3. It's a very long process. It's not quick like a 2x2. Very, very easy to make a mistake. So I'll show you how to check your answer. Maybe I'll make a mistake and I'll show you what I would do if that was the mistake. So that could happen. Sometimes it doesn't happen. So when we get to checking our answer and you notice that it's wrong, let's suppose it's a final exam and you can't find your mistake, you've run out of time, put a little note there and say that you know it's not the right answer. At least that's showing me that you knew that when you checked, you knew what you were talking about, okay? That's what I always hope to see. Anytime you're on a test and you checked your answer and it didn't work, and you know it didn't work, don't pretend it did. So someone will say, oh shoot, I got a 2. I'm just going to change it to a 1 because that's what I was supposed to get. Right? Leave it as a 2 and put a little note. I know that's supposed to be a 1. I've looked through and I can't find my calculation error. If all your process is right and your check is right and you've got a little note saying that, I actually give you 100%. If you've done it right. A little adding mistake, 4 minus 3, and you put a 2 by mistake instead of 1, in the first step will screw the whole thing up, right? But if your process is all right, you followed through, I look at your steps, and then if you didn't cheat in the end and try to pull one over on me, then I just give you 100% on the question. So do watch for that, okay? That's if your process is right. If I see that you went really wrong and your method was wrong and that's why it ended up wrong, of course you would lose marks for that. But if your method is right and all you've made is a little calculation error, I don't actually take off marks for that. Okay? What I'm testing is that you can find the inverse, right, or you know how. So a 2 by 2 is easy-ish. Use inverses to solve equations. So this is more likely where you would actually use an inverse. It is an operation, but it's used for something. So we use inverses to solve equations. So for example, if I said solve for x, all right, so this is saying solve for x. A, B, C, and x are matrices of size n by n. So what's that saying? There's some size that's square. So first of all, that's saying they could have an inverse. Maybe we would say are non-singular matrices of size n. Means they have an inverse, or the determinant's not 0, and they're square. And they're all the same size. Okay, so that means we can multiply them in either direction. We can add them, we can subtract them, and we can find the inverse. So how would we solve for x? Think of real numbers here, but as soon as you go to divide, you can't divide, because there's no such thing as division in matrices. So if these were real numbers, how would we solve it? Let's just do that off to the side. If these were real numbers, not matrices, and we had a times b minus c times x equals 0, we might do something like that. And then what would we do? Divide both sides by minus c? And we would say x is a b over c. Does that make sense? In real numbers, that's what we would do. And you can do all the same things in matrices, except you can't divide. So when you need to divide, you use the inverse instead. Okay, so I'll show you what that would look like. So let's say let's make them positive. You agree with that? The other thing you have to be careful not to do is switch them around. You can't, by mistake, write b times a or x times c, because the order is important. Now, normally I would divide by c, but we can't. So how to get rid of a c is to multiply by the inverse of c. So if we wanted to divide by c here, we do it to both sides. If we want to get rid of c here, we have to multiply by the inverse on both sides. So we're going to multiply both sides by c inverse. Now, where you put the c inverse matters. This is wrong. This is wrong. So I multiplied both sides by c inverse. But what's wrong with it? Right. If you want them in front, they have to be in front of both sides. Here I put it at the end of AB and at the front of CX. You can't do that. So that's wrong. So when we want it to be in front of the C here, to cancel it out, we actually need it in front of this. So C inverse times AB equals C inverse times CX.
Would it still be correct to put them at the end as well?
No.
No, not at all.
No, because you need it to be touching the C so that the C will cancel.
Okay, yeah,
right? If you put it at the end, it wouldn't be touching the C and you wouldn't get it to cancel. So we want it touching the C because what's C times its inverse? I. So now we have C inverse AB is equal to I times X. And what's I times anything? Itself, right? So this is C inverse AB equals X. So we've solved for X. X is equal to C inverse times AB. So if you had those matrices, you could find the inverse of C and multiply in front of AB in that order. C inverse times A and then multiply by B, or multiply A times B and then multiply by C inverse in the front. But you have to keep them in the right order. So we already talked about transpose in the earlier section and what transpose is, and the reason they put it in this section is because the properties of transpose and the properties of the inverse are actually the same. So this property says what? If you multiply A times B and then take the inverse. Okay, this is saying multiply A times B and then take the inverse. It would be the same as taking the inverse of each and multiplying them, but the opposite direction. Okay, so we actually have to reverse the direction. So this is a different property than real numbers, because in real numbers, if we had, for example, in real numbers, say we had 2x cubed, then we say this is 2 cubed times x cubed, and it really doesn't matter the order. So this would be 8x cubed, right? We put the exponent into both. But here, when it's an inverse, we have to reverse them to get the same answer. Okay? And that property is the same for transpose. So for transpose, if we take A times B and then transpose the answer, so you do the inside of X first and then transpose it, we could get the same thing by transposing them both, but in the reverse order. And for transpose, they don't need to be square. Right, for example, if we had, let's look at the transpose for a second. If let's say A is a 2 by 3 and B is a 3 by 1. Okay? So what size would A be? So the middle numbers match, and AB would be a 2 by 1. When we multiply it, we'd get a 2 by 1. And then if we transposed A times B, what size would it be? It's the opposite size, because we're switching the rows and we're switching the columns. So this would be a 1 by 2. Okay? So without even writing the matrices. Now what if we transpose them first? So remember, B is a 3 by 1, so B transpose would be a 1 by 3. A is a 2 by 3, so A transpose would be a 3 by 2. Now look at how you can multiply them. Which one has to come first if you were to multiply the transpose? Right, so A times B transpose, you can multiply them first because the numbers match, but when you do the opposite, you have to have B transpose first for the size to work. Okay. So if you multiply them and then transpose, it's the same as transposing them both and then multiplying, but in the opposite order. And the inverse works the same way. Okay. So those are two properties. And you could show that if you had an A and a B, you could find the inverse of both, and then you would show each side that were equal. All right. So I didn't do it with an example, I just sort of talked through, but you could actually be given an example and be asked to show a property, you know, using this particular A and B. So, let's write that down. That's what I mean. You could be asked to show that if A is equal to so here's an A and a B. So the left-hand side, A, B inverse, says find A, B first. Uh, 2 plus 6. Uh, 24 minus 4, 20. I've got my answer here. I'm hoping someone's doing this at the same time. Okay, so there's A times B. It matches what I have here, so let's assume it's right. So I didn't show you all the actual multiplications. You should be able to do that. Now what? We need to find the inverse. So the inverse is 1 over the determinant, and then we switch these and change the sign of these. So we just need the determinant. 2 times 8, main diagonal. Oops, sorry. That was not right. The determinant of AB, sorry. So 8 times 20 minus 20 times 7. So just 20. 8 20s minus 7 20s. And you could leave it like this if you wanted with the number factored in front, or you could put it in. Okay, either way. So if we put it in, we would have 20 over 20 minus 7 over 20 minus 20 over 20 and 8 over 20. And this is what I mean. I would just leave those both over 20 instead of reducing one, because if you're going to check it or use it to multiply or do anything with it later, it's better in a common denominator. And I don't, the number's the right number. It's just not simplified, but it's still the right answer. So I would just leave it like that. Okay, so that's the left-hand side. Now what about the right-hand side? So the right-hand side says B inverse times A inverse. So we need to find both inverses and then multiply the answer. So B (1 minus 1, 2, 3). So to find the inverse, we need the determinant. 1 times 3 minus negative 1 times 2 is 5. Switch the 1 and the 3 and change the sign of the other two. So there's B inverse. I'll just label it there so I remember. And then we need A inverse. Two times 8 minus 3 times 4 is 4. So 1 over 4, switch the 2 and the 8. And change the signs here. You could leave that, or switch it to a half. Okay, so there is our inverses separately, and this side said B inverse A inverse. Should give us the same answer as this. So B inverse times A inverse let me rewind a bit. Before you multiply that scalar in, this with the scalar is still the inverse. If you wanted to multiply these two, you could hold those scalars until the end. So you could save the 1/5 and the 1/4, and that would be 1 over 20 that you put in front of it. Okay, so that was one of the properties of multiplication, that you could move those. We're not going to. We'll just do it right through. So 3 over 5 times 2 is 6 over 5, minus 1 over 5 is 5 over 5, which is 1. Where are we supposed to get a 1? Yeah. So 3 over 5 times minus 3 over 4 plus 1 over 5 times 2 over 4. So this will be minus 9 over 20 plus 2 over 20 is minus 7 over 20. So far, so good. And then the second row, minus 2 over 5 times 2 plus 1 over 5 times minus 1 gives me minus 4 over 5 minus 1 over 5, minus 5 over 5, which is negative 1. And then the last one, oh, I don't have room here, but minus 2 over 5 times minus 3 over 4 plus 1 over 5 times 2 over 4. 6 over 20 plus 2 over 20 is 8 over 20. Okay. And I didn't reduce the fractions, and I think that makes it a little easier. You have the same denominator. Okay. So even though 2 over 4, I was really tempted to write that as 1 over 2, because that was easy to reduce, I still didn't, because when you multiply things, if you have the same denominator to start with, it is easier. So the answers were the same. So you would conclude AB, therefore AB inverse equals B inverse A inverse, which equals 1, negative 7 over 20, negative 1, and 8 over 20. So you need a little conclusion if you're asked to show something. Okay, so we did both sides. Sometimes I would just, if they didn't take this much room, I would have put a big arrow between them and said they're equal and put it up here, equal. But if you can't do that easily, then a new line saying they're equal is sort of a conclusion, okay? All right, so the next part of inverses is that we use inverses to solve a system of equations. So we did solve systems of equations already, and that's when we were solving for x and y, or we did it with a and b's. Right? We used elimination, which was make, say, the coefficient or the number in front of the a the same with the opposite sign, and then we add them together. That got rid of the a, then we plugged it back in. That was elimination. So you can actually use the inverse to solve systems. We can use the inverse to solve systems of equations. All right, so here's an easy to solve system, okay? And we know how to do it. And I'm going to show you this for 2 by 2. You would never do it because it's longer than doing what we already know how to do. But when it comes to 3 by 3 and 4 by 4, 5 by 5, once you know the inverse, it's just one multiplication to get the answer. You don't have to go through the whole elimination part. And remember when we were trying to solve a system when it was 3 unknowns and 3? You eliminate one variable, then you plug that into the other 2, then you eliminate a variable, and then you take that answer, and it got confusing. The inverse method will help to do it quicker. Okay, so you do have to find the inverse, which is a long process, for bigger than a 2 by 2. But once you have the inverse, you can solve lots of systems with it by just doing one multiplication. So in computers, that's an efficient way to do it because the amount of work is just one multiplication rather than resolving a whole system. And in companies, what they would do is have sort of, say you had a recipe to make a certain type of paint or something, okay? So the system itself would hold the numbers in the recipe. Say 2 cups of white paint, 0.5, right, of this pigment. So the actual, this part would hold the sort of recipe, and over here would be how many cans you wanted to make of each, suppose. If you wanted to change just these numbers, all you need is the inverse once for that system, for that recipe, and then it just takes a quick multiplication, you've solved a new system. Change the numbers again, a quick multiplication, you've solved a system. And a computer can do a matrix multiplication really fast. So you can solve a whole bunch of systems really quick with an inverse. Now, if you want to change the recipe, then you have to find the whole new inverse. So that's maybe not the most efficient way, but that's where we would use it. All right, so how do we do this? So step 1, write the system in AX equals B form. Let's call that a capital B. X isn't. So in section 2.1, we talked about the different forms you could write systems in, and this was one of them. So AX equals B form is taking your A, which is your coefficients of the X and the Y, so 2 minus 3, 2 minus 2, so that would be A. X is your variables, equals B is your right-hand side. This is just a multiplication. If we were to multiply, I'm just going to write it off to the side because I don't want to mess that one up. If we multiply, you take row 1 and you multiply it by column 1. So you'd have 2 times X plus minus 3 times Y, and that gives you this, 2X minus 3Y. And if you did row 2, you would get 2 times X minus 2 times Y. It's a matrix multiplication. Okay, so putting it this way makes the size work out, 2 by 2, and this is a 2 by 1. Right? So that's AX equals B form. So that's step 1, is to write it in the right form. Step 2 is to find the inverse of A. So this only works when you have 2 unknowns and 2 equations, or 3 unknowns and 3 equations, 4 unknowns and 4 equations. So we find A inverse. Now what do we do with that is we solve for X. So we have AX equals B. how do we solve for x in matrices? You can't divide by A. So what do? Instead of dividing, you have to multiply by the inverse. Has to go in front because it has to touch what you want to get rid of. So here you would multiply by A inverse. On both sides. Remember at the front, if you're doing it at the front. What does this give us? I, which is just x, because it's like multiplying by 1. So if we know the inverse, then we can, to solve for x, to find the solution to the system, we can take the inverse and multiply by the right-hand side, and that will give us the answer. That's what this is saying. So, find A inverse, then find A inverse times B, and that gives x. And that could work for any size. So if the system was huge, you would find the inverse and then just multiply by the right-hand side. That would give you the answer. It's kind of restrictive, so it's not a good method. Restrictive in that if the matrix doesn't have an inverse, it won't solve the system. Although the system could be solved, it won't find your answer because you can't find the inverse. So it's restrictive and it doesn't find all the possibilities. But if it has an inverse, if the matrix is not singular, then you can solve the system this way. All right, so let's do one. So, not using regular elimination, but using the inverse method, let's solve the system. So, write down the system in AX equals B form. So, putting it into a matrix. This would be A. So, we're going to find A inverse. That's our formula. So, the determinant of A is 2 times minus 2 minus negative 3 times 2. So the determinant of A is 2. Switch these, so negative 2 and 2, and change the sign, so 3 and minus 2. So we could check to make sure we did the inverse right. How would you check that? Multiply by A. This is a guaranteed full marks question on any exam because you can check your work along the way and then go back and fix it if you messed up. You know if you've got the right answer. So you could check multiply A times A inverse or A inverse times A. It doesn't matter which direction. And you should get I. Okay, so I just multiplied them and we get the identity. So far, so good. Then what do we do with the inverse? So x is equal to A inverse times B. So A inverse. And what's B? 1, 3. Multiply. 1 times minus 1 plus 3 over 2 times 3. And then minus 1 times 1 plus 1 times 3. All right, so here's x, which would be xy. So x equals 7 over 2, y equals 2. How do we check, how do we check that? Plug it into the original, just like you would normally do when you solve a system. So we can check here. We know that's right. If this doesn't work in the original system, then our mistake was here. Right? You could go all the way through and just check this, but then you would not know if your mistake was here or here, right? But then you could check that, say, okay, my inverse was right, my mistake must be here. So you can check this answer as well. So 2x minus 3y equals 1. So 2 times 7 over 2 minus 3 times 2. So it works in the first equation. So 2 times 7 over 2 minus 2 times 2 is 7 minus 4 is 3. Works in the second equation. Check both, because you could have made one correct and the other one, the multiplication, wrong. So usually it will either work in both or not, but I have seen people fluke into an answer that works in one equation and not the other. So make sure you check both. Okay. So there's our solution. I usually on a question, like on a test, would say, and check your answer, and the check I actually make worth a mark. So show the check, don't just check it and say it's right, like actually show it, like I did here, to get that mark for checking it. Yep.
Is there only one property, the transpose and inverse?
No. I must have them here somewhere. Okay. So, let's see, we're almost done. So what would be the drawbacks of this? I sort of said it. If the matrix is singular, we can't solve it. But what would that mean if the matrix was singular? Any ideas? So remember when I said there were systems, so you can have, these are 2 by 2, so these are just lines like we draw in school. So a 2 by 2 has one solution, like this one. And what does that mean about it? It means the 2 lines crossed at one point. That was the point where the 2 lines, if you were to draw the 2 lines, they cross at that point. If the lines are parallel, let's write one that's parallel a system. So how do I make a parallel line? Remember, the slope has to be the same. I actually told you this is that if we multiply this by something, say 3, but don't multiply that one. Because if we multiply that, it would be the same line. But if we don't multiply that, like if I gave that 4 instead of 9, okay? So I multiplied. This would be the same direction vector. It's the same direction, but it has a different point that it attaches to. Right? So they're not, they have a different y-intercept. So they're parallel. If we go to find the determinant here, so we say, okay, A x equals B. Here's A. What's the determinant of A? 1 times 6 minus 2 times 3. No determinant. So of course you can't do 1 over 0 times anything, so that doesn't have an inverse. Does that make sense? So no inverse. Is there a solution to parallel lines? Have a solution? No, they don't cross. But could we get the determinant and actually have a system with a solution? Could the determinant is 0 and the system has a solution? Yes, when the lines are the same. So if we took that same first line, but when we multiply this one to get the second equation, I actually multiply the whole thing, so they are the same line. So any point, give me one point that's a solution to this system. There's infinitely many. One of them would be 1, 1. Does that work? 1 and 1. What about 3 and 0? Does that work? And remember, the second line is the same line, so it'll work in there too. Could I go on forever? Yeah, well, all I'm doing is plugging in a value of x and then solving for y. 1/2. Right? And so it does have solutions, but the determinant is 0. But this one has infinitely many solutions. So what does that say about the inverse method for solving a system? It's only good if
your lines aren't multiple of each other.
yeah, the inverse method only works to solve a system if the system has one unique solution. They cross at a point. Same with any other size. If it has a unique solution, then it can be solved by the inverse method, and if it doesn't, then it can't. So checking the determinant will not tell you how many solutions it has. It will just tell you it doesn't have one. Right? If the determinant is not 0, then the system can be solved and has one solution. If the determinant is 0, it may not be able to be solved, or it might have infinitely many solutions. You don't know. So it doesn't tell you that. In a 2x2, we could just look at it and tell, but later on we can't. So here we see, oh, the determinant's 0. I could look back and say, well, this has infinitely many solutions because I can see they're the same line. And here this has no solution because I can see they're not the same line, but they're parallel. But with 3x3s and bigger, you can't tell by just looking at it. All right, so properties. Here they are, the list. Okay, so we knew the first one. Number 2. We saw that one and we guessed what that was earlier. Take the inverse and then the inverse again. You get back to the start. We saw this one. What's that?
B.
B inverse times A inverse. What about this one? What do you think? Yeah, C inverse, B inverse, A inverse. And that one worked for transpose as well. And if there was 3, you would do the same thing. This, if you can add 2 matrices and then take the transpose, if you transpose them first and then add them, it will work. Inverse doesn't have this property. So that's just for transpose. So you can transpose and then add, or add and then transpose. This one is for transpose as well. Does not work for inverse. Okay, we'll talk about what happens is the determinant changes by a factor of 3, like, yeah, like if you multiply a matrix by 2, the determinant doesn't change by 2, it actually changes, if it was a 3 by 3, it would actually change by 2 times 2 times 2. So this property does not work for inverses. It would change it by more. These ones are just for transpose. What do you think? Transpose and then transpose it again? Back to itself. I could have written that one up there. And 7, A transpose inverse. A inverse transpose. Why would that be useful? Well, if you had 2 matrices and they were the transpose of each other, you only need to find the inverse and transpose it. Do you want me to say that again? If you had 2 matrices that you wanted to find the inverse of, say find A inverse and B inverse. Suppose A is 1, 2, minus 1, 3. And B is 1, 2, minus 1, 3. And you want to find the inverse of both of those. If you noticed that A and B are transpose of each other, then you only need to do the inverse once. So A inverse would be what? 1 over the determinant of A, 3 minus, and minus 2, so 5. So there's A inverse. You could check it to make sure it's okay. But notice that A transpose